Welcome. Tonight, we journey to one of the strangest and most fantastic periods our planet has ever known. A lost world where dragonflies the size of seagulls soared through the skies, and creatures the size of cars crawled across the forest floor. This was an age of steam and swamps, an age of giant insects, and it existed long before the first dinosaur. On this journey, we will explore the profound mystery of how these incredible creatures grew to such colossal sizes. We will investigate the unique moment in time when the planet's very atmosphere became a superpower, and why, after their spectacular reign, they vanished silently from the Earth. So, before you get comfortable, take a moment to like the video and subscribe, but only if you genuinely enjoy what I do here. And let me know in the comments where you're tuning in from and what time it is for you. It's always fascinating to see who is joining us from around the world. Now, dim the lights, maybe turn on a fan for that soft background hum, and let's ease into tonight's journey together. When you hear the word prehistoric, your mind likely conjures a lush jungle trembling with the roar of a Tyrannosaurus, or a landscape where a Brachiosaurus calmly pulls leaves from the treetops. But our world tonight is hundreds of millions of years older than those familiar scenes. This is a world before a single dinosaur had yet evolved. I am taking you to the Carboniferous period, roughly 300 million years ago. This was a global swamp world where the trees were not like our trees, but giant, bizarre ferns and towering scale-barked plants. But the true rulers of this world were not the plants. The very air here was different, thick, humid, and supercharged with a gas at a level we can scarcely imagine today: oxygen. And in this supercharged atmosphere, one of the planet's most humble groups of creatures, the arthropods, grew to sizes that defy our imagination. This was a world where Arthropleura, a giant armored millipede, prowled the forest floor like a crocodile, where Pulmonoscorpius, a scorpion the size of a dog, hunted its prey, and where Meganeura, a dragonfly with the wingspan of a hawk, dominated the skies. Tonight, we journey deep into this strange, forgotten forest, into its steaming mists, to unravel the mystery behind the rise and the fall of the giant insects. The world that these giant insects were about to inherit was itself born from the death of a previous one. For tens of millions of years, as we explored in our last journey, the continents had been ruled by a different kind of giant, a silent kingdom of towering grey columns that stood like lonely monuments against a hazy sky. This was the age of Prototaxites, the great fungal empire. This long, quiet reign was not an end. It was a transition. It was the great preparation. The fungi had been the planet's silent architects, patiently and slowly turning the barren, rocky dust of the continents into a rich, dark and fertile soil. They had helped to stabilize the climate, drawing down carbon from the atmosphere. They had, in their own patient way, built a home that they themselves were not destined to keep. Because, while the fungi ruled in their slow, static way, a green revolution was mounting. In the damp river valleys, the plant kingdom was forging the weapons it needed to conquer the land. Plants developed vascular tissue, an internal plumbing system to move water. They developed strong, true roots to anchor themselves and drink deeply from the new soil. And most critically, they developed lignin, a hard biological polymer that allowed them to build strong, woody stems and grow tall, beginning a great arms race for the sky. The most formidable of these new warriors was Archaeopteris, the world's first true tree. It formed the first great forests, its fern-like fronds interlocking high above the ground, casting the world below into a new and permanent shade. This green tide, this new world of the forest, was a catastrophe for the fungal giants. They were starved of light from above and outcompeted for resources in the soil below. One by one, the silent columns fell, and the fungal empire gave way to the empire of the trees. The world became a place of dappled light, of damp earth, and the constant, soft rustle of fronds and leaves. This was the victory of the plants. It was total and absolute. But this victory, this new green world that had triumphed over the old, had a profound and unintended consequence. The very biology that had made these new trees so successful was about to trigger a chain of events that would alter the very air we breathe. It would unbalance the planet's delicate systems, and in doing so, it would set the stage for an age of giants even stranger than the ones that had just vanished. The victory of the forests was absolute. This new green world was lush, humid, and teeming with the promise of new life. But in its triumph, it had also created a profound planetary scale problem, a fundamental imbalance in the great cycle of life and death. The problem, ironically, was born from the very innovation that had given the trees their strength. It was a problem called lignin. We have spoken of lignin as the biological concrete that allowed plants to achieve height. Let us pause for a moment to appreciate what this truly means. Lignin is a complex, dense, and incredibly tough organic polymer. It is the substance that gives wood its strength, its rigidity, and its profound resistance to decay. It is, molecule for molecule, one of the most resilient materials ever produced by life. It was a biological masterpiece of engineering. In our modern world, when a tree falls in the forest, it does not last forever. It is immediately and relentlessly set upon by a vast, invisible army of decomposers. Specialized fungi, like the white rot fungi and countless bacteria have, over the last 300 million years, evolved an equally complex arsenal of enzymes, a specialized chemical toolkit designed for one purpose: to unlock and break down the tough, stubborn bonds of lignin. They are the great recyclers, the janitors of the forest, ensuring that the carbon and nutrients locked in that wood are returned to the soil to fuel new life. But back in the Carboniferous period, this was not the case. Lignin was a brand new invention. It was a biological safe, and the combination to unlock it had not yet been evolved. The trees had created this incredible, durable armor. But the decomposers, the bacteria and the fungi of that time were utterly baffled by it. They simply did not have the chemical keys to dismantle it. And so, for millions of years, when one of these giant, primitive trees, like a towering 100-foot lycopod or a colossal horsetail, lived its life and finally fell, it did not rot. It did not decompose in the way we understand today. Instead, it just stayed. It fell into the soft, muddy floor of the great global swamps, and it sank. The stagnant, oxygen-poor water of the bogs would pickle and preserve the wood, further inhibiting any small, primitive bacteria that might have tried to break it down. Imagine this process on a global scale. Generation after generation, century after century, a new, thick layer of dead, unrotted wood would fall upon the last, piling up in deposits that were hundreds of feet thick. It was a one-way trip for carbon. This process became a colossal planetary engine. The living forests were acting as a global pump, pulling carbon dioxide from the atmosphere through photosynthesis. They locked that carbon into this new, nearly indestructible material called wood. And then, when they died, they buried it deep in the earth, taking it out of the system forever. The planet was, in effect, holding its breath, sequestering millions of tons of carbon with every passing millennium. This massive, global burial of undecayed wood was about to have two world-altering consequences. First, it was about to scrub the atmosphere of its carbon dioxide, changing the climate. And second, as a direct byproduct of all that non-stop, unrecycled photosynthesis, it was about to release a flood of another gas, a waste product that would supercharge the world and set the stage for an age of giants. To understand what happened next, we must think of the entire planet as a single, breathing organism. In a normal, balanced world, this breath follows a perfect, steady rhythm. In the daylight, the planet's green lungs, its forests and algae, inhale carbon dioxide and exhale oxygen. This is photosynthesis. Then, at night and in every moment of decay, the planet exhales as organisms, animals and decomposers alike, take in that oxygen and release carbon dioxide back into the air. This is respiration and decomposition. Inhale CO2, exhale O2, inhale O2, exhale CO2, a perfect closed loop. A beautiful planetary equilibrium where every atom is accounted for and recycled. But the Carboniferous period, with its strange, unrotting trees, broke this ancient rhythm. It shattered the equilibrium. The burial of all that lignin-rich wood was a geological event of profound significance. It was like a ratchet, a one-way street for the planet's chemistry. Think of it this way. The planet was taking its great inhale, pulling in vast, continent-sized breaths of carbon dioxide to build its new forests. But it was not exhaling. The second half of the cycle, the part where decomposers would normally break down the wood and release the carbon back into the air, was broken. The carbon was being locked away, buried deep in the silent, dark swamps. This had two simultaneous world-altering consequences. First, the inhale was now all one way, with millions of tons of carbon dioxide being pulled from the air and never returned. The atmospheric concentration of CO2 began to plummet. The thick, warm greenhouse blanket that had wrapped the planet for eons began to thin out. The planet's great heat-trapping engine was failing. As a result, the world began to cool. This wasn't a sudden snap, but a long, slow chill, a gradual transition out of the ancient greenhouse and into a new, cooler and more dynamic climate. The second consequence was even more dramatic, and it was the direct result of all that one-way photosynthesis. Oxygen. In a normal cycle, the oxygen released by plants is used up by the animals and decomposers that eat them. But now, the plants were being buried, not eaten or decomposed. And all the oxygen they had created as a waste product during their lives was left behind in the atmosphere, with no corresponding process to consume it. It just accumulated. With every millennium that passed, the global concentration of oxygen crept higher and higher. The very air of the planet, the invisible ocean in which all life existed, was being fundamentally rewritten, molecule by molecule. It was a slow planetary alchemy, transforming the atmosphere from a thick, carbon-rich soup into something thin, cool, and charged with a new and potent gas. The air itself was becoming a different substance, a substance that would create a climate unlike any that had come before, a world of steam and mist and endless dripping swamps. This new atmosphere, scrubbed of its CO2 blanket and flooded with oxygen, did not just alter the planet's chemistry, it altered its very character. The long, stable, quiet greenhouse of the Devonian world was over, and in its place, a new, more dynamic and unstable climate was born, the world of the Carboniferous. The plunging carbon dioxide levels meant the planet no longer had its thick, insulating blanket. The world was cooling. On the vast supercontinent of Gondwana, which was still straddling the South Pole, for the first time in tens of millions of years, immense ice caps began to form. Glaciers, miles thick, ground their way across the rock, locking up inconceivable amounts of the world's water as ice. This single fact, the new presence of polar ice, became the great environmental engine of the age. It put the planet on a geologic pulse. As the ice caps grew, sea levels would fall, exposing vast new areas of coastal land. When the climate warmed slightly and the ice caps retreated, the sea levels would rise again, flooding those same lands in shallow, warm water. This rhythmic, constant fluctuation of rising and falling seas was the perfect machine for creating the dominant biome of the Carboniferous, the great global coastal swamp. Now, let us paint a picture of this new world. Imagine a landscape that stretches for thousands of miles, a territory larger than entire continents today, that is neither true land nor true ocean. It is a vast, flat, waterlogged forest. The air is so thick with moisture that a permanent, steaming mist hangs between the colossal, alien-looking tree trunks. The atmosphere is oppressive, humid and heavy, a world of perpetual, dripping dampness. The ground itself is not solid. It is not the rich, loamy soil that the prototaxites had begun to build. Instead, it is a deep, spongy and treacherous mat of unrotted plant matter, a substance we now call peat. With every step, a dark, acidic water would squeeze up around your feet. This acidic, oxygen-starved water was the key. It was a perfect tomb, instantly pickling and preserving any plant that fell into it, which in turn locked even more carbon out of the sky. This was the Great Coal Swamp, a boundless, horizontal world of stagnant water, towering, primitive trees, and a constant, pervasive mist. And hanging over all of it, in every breath, was the single most important ingredient of this new age: the air. The air was thick not only with moisture, but with that vast, unrecycled surplus of oxygen. It was an atmosphere that was denser than our own, and richer in a gas that is the very fuel of energetic life. This supercharged air was a potent, invisible force that would have profound consequences. It was a world that felt electric, a world on the verge of something. It was an evolutionary laboratory, about to test the absolute limits of what was possible for one group of creatures, a group that was perfectly poised to take advantage of this strange, new and oxygen-rich world. The stage was now set. The great global swamps with their alien, towering trees steamed in a new, cooler climate. And the air, that invisible ocean in which all this life was suspended, was now fundamentally different. We must pause here and truly appreciate what this meant, because this single fact is the key to unlocking the entire mystery of the giant insects. Today, our atmosphere is a comfortable, stable 21% oxygen. This is the balance that our lungs and the lungs of every animal on Earth are perfectly tuned to. In the great coal swamps of the Carboniferous, that number climbed. It climbed past 25, past 30, and perhaps during its peak, it reached an astonishing 35%. This was not a trivial difference. An atmosphere at 35% oxygen is a different substance entirely. It is a supercharged world. For all complex life, oxygen is the trigger. It is the draft that fans the metabolic fire. It is the gas that allows our cells to unlock the energy stored in food. And the Carboniferous world was like a blast furnace. Every breath an ancient creature took would have delivered a jolt of pure, high-octane fuel, a rush of energy far more potent than what is available to any creature today. A simple act, like digesting a meal or moving a muscle, would have been more efficient, more powerful. This was a world where energy was cheap. This super-oxygenated air was also physically different. It was denser, it had more substance, more grip. For any organism that was attempting to master the sky, this was a profound gift. Flying in this thick, rich atmosphere would have been easier, like swimming through a more buoyant liquid. It would have provided more lift for every beat of a wing, allowing for larger and heavier bodies to stay aloft with far less effort. But this supercharged world, so full of energetic potential, was also a world of incredible, pervasive danger. It was a planetary tinderbox. We know how easily a fire can start in our 21% oxygen world. At 35%, the world was flammable on a scale we can scarcely imagine. Even damp wood would burn. A single lightning strike, cracking through the humid air, would not have just started a forest fire. It would have triggered an inferno, a near-explosive conflagration that would have raced through the swamps with terrifying speed. The very air itself was an accelerant. The constant, damp, misty nature of the swamps may have been the only thing that kept the entire world from burning to the ground. This new, potent and dangerous atmosphere was an evolutionary opportunity, a blank check written by the planet itself. But it was an opportunity that not all life could seize in the same way. The amphibians of the time, our own distant ancestors, were limited by their simple lungs and their need to stay close to water. No, this invitation to greatness was aimed at another group. A group that, until now, had been small, humble, and scurrying in the shadows of the world. They were the arthropods, the creatures with their skeletons on the outside, and they were about to use this invisible, high-octane fuel to step out of the shadows and grow to a size that the world would never, ever see again. The age of the Titans was about to begin. Let us begin our tour of this strange, supercharged world on the floor of the great coal forest. We must move slowly here, our feet sinking into the damp, spongy peat with every step. The air is thick, misty, and carries the heavy organic scent of decay and fermentation. High above, the alien canopy of the scale trees and giant ferns filters the light into a deep emerald twilight. And here, in the dim undergrowth, we must watch our step, because we are not alone. Something is moving through the giant fallen logs and the groves of towering horsetails. It is not a reptile, and it is not an amphibian. It moves with a strange, multi-legged, rhythmic fluidity, its immense body winding its way over the terrain. This is Arthropleura, the largest land-dwelling invertebrate that has ever lived. It is a creature that defies our modern sense of scale. Imagine an animal that is, in essence, a millipede, but a millipede that has grown to the size of a modern crocodile or a small car. The fossil record, the long segmented tracks it left behind in the ancient mud, shows us a creature that could grow to be over 8 feet or 2.5 meters long and perhaps 2 feet or half a meter wide. It was a true titan of the forest floor, a living, armored train. Its body was long, flattened, and composed of roughly 30 overlapping segments, each one a hard, chitinous plate. This was its exoskeleton, its suit of armor, which would have glistened darkly in the misty light of the swamp, perhaps a deep, mottled brown, or a shiny, intimidating black. Running down its back were 2 rows of raised bumps and ridges, giving it a rugged, almost ornamental appearance, while its flanks were protected by pointed side plates that flared outwards, like the armor plating on a tank. And beneath this imposing chassis, a forest of legs, dozens upon dozens of pairs of legs, moving in a constant, hypnotic, rippling wave, propelling the giant's immense weight forward over the soft, uneven ground. To see it move would have been a mesmerizing and perhaps deeply unsettling sight, a perfect, silent, fluid motion, the ground trembling slightly under its passage. Its head, by comparison, was small, tucked beneath the front of its armored plating. It had a pair of segmented antennae, constantly tasting the thick, humid air, sensing the chemical world of the swamp floor around it. This was the undisputed king of the undergrowth, a creature whose sheer size would have left it with no natural predators in its time. It was an armored, multi-legged behemoth that was only possible in this strange, forgotten world. Its discovery, a story of scattered pieces and giant footprints, would slowly reveal the scale of a creature that seemed to have crawled directly from a nightmare, forcing scientists to ask a very simple, baffled question: what was this thing? It is a natural and easy thing to look at this colossal, segmented, many-legged creature and to simply label it in our minds: a giant millipede. Our brains search for the familiar, for a box to put this monster in, and the millipede in our garden is the closest one we have. And for a long time, that is exactly what scientists did. But in the quiet, patient halls of paleontology, "looks like" is a very dangerous phrase. The book of life is full of strange coincidences, of creatures that arrive at similar solutions from very different starting points. And the precise identity of Arthropleura has been a long and subtle debate. What, after all, makes a millipede a millipede? The name itself, thousand legs, is a romantic exaggeration. The true defining feature of the group, the Diplopoda, is in their very name. Diplo means double, and poda means feet. True millipedes have a fused body plan, where each visible segment is actually two ancestral segments merged into one, giving them two pairs of legs for each segment. This is their unique evolutionary signature. The question then was simple. Did Arthropleura have this double foot arrangement? The answer, frustratingly, was hidden by the fossils themselves. The remains of Arthropleura that we find are spectacular, but they are almost always incomplete. What we have in abundance are the backplates, the hard, durable, chitinous armor that covered the creature. These segments, called tergites, preserved beautifully in the fine-grained mud of the coal swamps. But the delicate legs, the soft underbelly, and the fragile head structures? These are almost never found. The fossils are like the discarded armor of a warrior, with the warrior long gone. It is like finding the magnificent fossilized shell of a turtle and trying to guess the exact shape of its head and feet. Without the complete picture, the debate was open. What we do have are its footprints. In the 300-million-year-old rock, in the places that were once the soft, damp floor of the forest, Arthropleura left its mark. These fossilized trackways, known to science as diplycnites, are breathtaking in their own right. They show long parallel rows of tiny footprints, sometimes over a foot wide, a silent record of the creature's rhythmic, rippling gait. These tracks prove without a doubt that it was a myriapod, a many-legged creature, but they are often too blurred by the ancient mud to clearly show whether the legs were arranged in single or double pairs per segment. And so, the quiet debate continued. Some scientists, looking at the general shape and the sheer number of legs, argued that yes, it was simply a true millipede, a member of the Diplopoda that, thanks to the oxygen-rich air, had achieved a truly spectacular size. Others, more cautious, suggested that it was something even more unique. Perhaps it was a close cousin, a related lineage that branched off before modern millipedes evolved. They gave it its own, distinct class, the Arthropleuridae. In this view, it was not a direct ancestor but a granduncle, a different and ultimately failed evolutionary experiment in what it means to be a many-legged creature. For our journey, the precise label is perhaps less important than the reality. It was a titan, an arthropod of a kind that the world had never seen before and will never see again. Whether it was a true millipede or a close relative, it was the undisputed armored king of the Carboniferous floor. But this classification puzzle only leads to an even more fundamental question. This giant, armored, 8-foot-long creature, what did it eat to fuel its immense size? The image of an 8-foot, armored, multi-legged creature crawling through a dimly lit swamp is a powerful one. It is a creature born from the landscapes of our nightmares. And our first primal instinct is to imagine it as a terrifying predator, a silent hunter of the Carboniferous floor. A creature of that size, with that much armor, must surely have been a fearsome carnivore, perhaps preying on the large amphibians or other invertebrates that shared its misty world. It is a terrifying thought, but is it true? For paleontologists, this question, what did it eat, was one of the deepest parts of its mystery, and the answer was, for a very long time, incredibly elusive. The primary evidence, the fossils themselves, were of little help. As we've learned, we have the magnificent tank-like body armor, but we do not have a well-preserved head. We lack the crucial evidence of its mouthparts. If we had found a fossil with giant, piercing, sickle-like mandibles, the case would be closed. But we have not. And so, for decades, scientists could only speculate, building a case based on inference. Perhaps it was a hunter, or perhaps, like its smaller millipede relatives, it was a decomposer, a herbivore. The mystery remained. The definitive clue, the smoking gun, came from a discovery in Scotland. It was a fossil of Arthropleura that was special not just for its preservation, but for what was inside it. Within the area where the creature's digestive tract would have been, scientists found a dense fossilized mass of its last meal. And what was in its gut? Not the bones of amphibians, not the crushed armor of other arthropods, but a compressed, rich collection of plant matter. Specifically, they found the spores and tissues of the giant club mosses, the very scale trees that formed the canopy of the forest. This single discovery transformed our understanding of this giant. The evidence was clear. Arthropleura was not a predator, it was a vegetarian. This new evidence allows us to paint a much different and perhaps a much more peaceful picture of this ancient giant. It was not a tyrant, it was a gentle giant. Imagine it now, not as a hunter, but as a slow, patient processor of the forest floor. It was the great recycler of its age, a creature perfectly adapted to consume the vast quantities of unrotted plant litter that carpeted the swamp. Its immense size and power were likely not for hunting, but simply for moving, for bulldozing its way through the thick, spongy and obstacle-ridden undergrowth. It was, in effect, a giant earthworm with armor, a colossal compost machine. It would have moved through the damp peat, its many legs gripping the ground, its head likely lowered, consuming the rich, semi-decayed fronds of ferns and the fallen trunks of the lycopod trees. It was an essential part of its ecosystem, an organism that was taking this dead, locked-away plant matter, breaking it down and returning its nutrients to the soil. So, the king of the Carboniferous floor was not a monster to be feared. It was a quiet, unassuming and vital gardener, the largest decomposer the world has ever known. But this gentle giant was not the only titan in the swamp. Other, smaller creatures were prowling the undergrowth, and these creatures were not interested in eating plants. They were hunters, pure and simple, and they came equipped with one of the most ancient and effective weapons on Earth. The great armored Arthropleura may have been a peaceful gardener, but the floor of the Carboniferous forest was not a realm of complete tranquility. There were other giants here, lurking in the damp shadows of the giant ferns and fallen logs. And these creatures were not built to consume the dead. They were built to hunt. Let us travel for a moment to the rock formations of what is now Scotland. Here, in the early 1990s, paleontologists unearthed a fossil that confirmed the existence of a true Carboniferous nightmare. It was a creature that was instantly, terrifyingly familiar. It was a scorpion, but it was a scorpion of a scale that the modern world has never known. Its scientific name is Pulmonoscorpius kirktonensis. The name itself tells a story. Pulmo is Latin for lung, and Scorpius is, of course, scorpion, the breathing scorpion. It was given this name because the fossil was so beautifully preserved that scientists could see its breathing organs, its book lungs, which were remarkably large, a clear adaptation to its environment. And what made Pulmonoscorpius so spectacular was its size. When we picture a scorpion today, we think of a creature that fits in the palm of a hand, a small, creeping threat. Pulmonoscorpius was a monster. It is estimated to have grown to 70 centimeters, or well over 2 feet, long. Imagine for a moment a scorpion the size of a domestic house cat, a creature that would have been as long as your arm. In every other respect, it was a scorpion, perfected and scaled up to an absurd degree. It had the classic menacing silhouette, two large, powerful claws, or pedipalps, at the front, held ready to grasp its prey. It had 8 sturdy legs to carry its heavy, armored body over the swampy ground, and it had that long, segmented tail arcing over its back, ending in a large, sharp, and undoubtedly venomous stinger. Unlike the gentle Arthropleura, Pulmonoscorpius was an apex predator of the undergrowth. With its combination of size, strength, and venom, it would have been a formidable hunter, a terror of the forest floor. It would have prowled the damp peat, its senses on high alert, perhaps using the fine hairs on its legs to detect the vibrations of approaching prey. What was on its menu? It likely hunted other large arthropods, perhaps even the smaller, juvenile Arthropleura, but it may also have been one of the first creatures on Earth to prey on vertebrates. The swamps were filled with the first small amphibians and early reptiles, creatures that would have been a perfect meal for a predator of this size. It would have seized its victims in those powerful claws, a grip of crushing chitinous armor, and then delivered a final fatal sting. And how could such a creature exist? How could it grow to a size that seems so impossible to us today? Once again, the answer was in the air. A modern scorpion's book lungs are a relatively simple, inefficient respiratory system. They work perfectly for a small creature, but they create a bottleneck that strictly limits its size. In our 21% oxygen world, a cat-sized scorpion would suffocate under its own weight. Its simple lungs just couldn't deliver enough oxygen to its body. But in the 35% oxygen of the Carboniferous, that bottleneck was gone. The supercharged air flooded its simple lungs, delivering high-octane fuel to every cell in its body. The atmosphere itself was a performance-enhancing drug, removing the biological limits and allowing the scorpion to evolve to a size that the world had never seen before, and will never see again. The forest floor, then, was a land of titans, both gentle giants and fearsome hunters. But the most spectacular realm of this supercharged world was not the ground. It was the air above. And to find the true kings of this age, we must look not to the land, but to the water, where the story of the greatest giant of all was about to begin. The titans of the Carboniferous were not confined to the damp forest floor. To find the origin of the most spectacular giant of all, the undisputed king of this entire age, we must leave the misty undergrowth of the scorpions and the millipedes and move to the water's edge. Imagine the countless pools and stagnant ponds that dotted this global swamp. They are not the clear, blue, sparkling lakes of our modern world. They are dark, tea-colored and acidic, choked with the decaying, unrotted leaves and fronds of the giant scale trees. The water is still, reflecting the strange alien canopy above like a black, rippling mirror. It is a drowned world, a network of dark, quiet pools, and it is a world that is teeming with its own hidden dangers. Here, in the murky depths, a different kind of life is unfolding. The giant dragonfly, Meganeura, did not begin its life in the air. Like all of its modern descendants, it was a creature of two worlds, and it spent the first and perhaps longest part of its life as a wingless, aquatic hunter. It began as an egg, laid by its mother on a submerged, rotting log. And from this egg hatched a creature that bears no resemblance to the elegant, winged jewel it will one day become. This is the nymph. It is a squat, broad, and heavily armored creature, a biological tank built for the underwater world. Its 6 legs are thick and spiny, designed to grip the sunken debris and crawl through the ooze at the bottom of the pond. Its color is a mottled, muddy brown and green, the perfect camouflage to vanish into the landscape of decaying leaves. This creature is not a gentle filter feeder. It is a predator, pure and simple, and one of the most ruthlessly efficient in the entire natural world. It is a silent, patient ambush hunter, and it is armed with a weapon that is like something from a science fiction film. Tucked beneath its head, held folded and out of sight, is a specialized, jointed lower lip. It is called a labium, but it is more commonly and more accurately known as the mask. This is not a simple jaw. It is a biological harpoon. The nymph will sit perfectly motionless for minutes, for hours, a picture of absolute patience, its eyes watching, its entire being focused on a single point, the moment of the hunt. When an unwary victim, perhaps a small primitive amphibian, a tadpole, or one of the first freshwater fish, drifts just a fraction of an inch too close, the attack is faster than the eye can follow. In a violent hydraulic explosion, the nymph shoots this mask forward, its toothed pincer-like end snatching the prey and dragging it back to its true, crushing mandibles. It is an ambush of terrifying, lightning-fast efficiency. And in the supercharged, oxygen-rich water of the Carboniferous, this nymph was not the small, inch-long predator of our modern ponds. It was a monster in its own right, perhaps growing as long as a human hand, or even larger. It was a top predator in its aquatic world, a nightmare in the water. For months, perhaps even for more than a year, this aquatic terror would hunt and grow, shedding its tough, armored skin multiple times as its body became larger and more powerful. It was accumulating the fuel, the mass, and the biological machinery it would need for its final great transformation. This underwater kingdom, for all its quiet menace, was just a prelude. It was a nursery, and the creature it was building was destined to leave this dark water behind, to break the surface, and to claim the new, open and oxygen-rich sky as its own. We have now met the titans of this lost age, the 8-foot armored millipede, the cat-sized scorpion, the hand-sized predatory nymph, and in our minds, a single persistent question must be forming, a question that is the central driving mystery of this entire era. How? Why did this happen? Why here in this strange, misty past, and why never again? Why in our modern world are there no land-dwelling invertebrates of this scale? A spider in our home may be unnerving, but it is small. A millipede in the garden is harmless. What fundamental law of nature changed? What biological switch was thrown in the Carboniferous that allowed these creatures to shatter the size barriers that so strictly limit their descendants today? The answer is not in their skeletons, or their muscles, or their diet. The answer, the entire secret, is in the air they breathed. And to understand why, we must first understand the profound and beautiful limitation that governs the life of almost every insect on Earth. The mystery of the giants is, in fact, a mystery of respiration. Let us think about how we breathe as mammals. Our system is an active, complex, and incredibly efficient engine. We have lungs, two great spongy bags, which we actively inflate and deflate, pulling air deep into our bodies. But our lungs are just the first stop. The oxygen we breathe is not delivered directly to our cells. It is transferred to a transport system, our blood. The hemoglobin in our red blood cells chemically bonds to the oxygen, and our powerful heart pumps this oxygen-rich fluid through a vast pressurized network of arteries and veins, delivering it with great force and precision to every single cell, from our brain to our fingertips. It is a high-pressure, active delivery, logistics network, and because it is so efficient, it scales. It works just as well for a mouse as it does for a blue whale. Now, let us look at an insect. An insect has no lungs. It has no heart that pumps oxygen. It has no blood that carries oxygen. Its entire respiratory system is a marvel of simplicity and a profound evolutionary dead end. An insect breathes through a series of small, passive holes running along the sides of its body. These holes are called spiracles. They are simply openings, like tiny portholes. And connected to each of these holes is a network of branching, silvery tubes called tracheae. These tubes branch and branch and branch again, becoming smaller and finer like the roots of a tree until they penetrate deep into the insect's body, delivering air directly to the muscle and organ cells. It is a passive, low-pressure system. The air is not pumped, it simply diffuses. It seeps in through the spiracles and travels down this network of hollow straws on its own. In our modern world, with its 21% oxygen, this simple system works perfectly, but only over a very, very short distance. The physics of diffusion are unforgiving. Oxygen molecules can only travel so far down a narrow tube in a given amount of time. This creates a hard biological ceiling. As an insect's body gets bigger, its internal cells get further and further away from the air supply. To compensate, the tracheal tubes would have to become wider and longer until, very quickly, they would take up so much room that there would be no space left inside the insect for muscles, guts, or any other organs. The creature would suffocate under its own unbreathable bulk. This is the fundamental law. In our world, the tracheal system is the great limiter. It is the biological reason why insects are small. But in the Carboniferous, the planet broke this law. It did not change the insect's anatomy. It changed the air itself. What happens to this simple, passive, and limited system when you flood it with an atmosphere that is not 21, but 35% oxygen? What happens when the air itself is so rich, so dense with fuel that it no longer needs to be pumped? It simply forces its way in. The supercharged air would have poured through the spiracles, saturating the tracheal system, diffusing deeper and faster, and with far more potency than ever before. The bottleneck was gone. The evolutionary barrier that had kept insects small for 100 million years was suddenly, totally and gloriously shattered. The ancient law was broken, and high in the misty, oxygen-rich skies, the result of this new freedom was about to take wing. The evolutionary barrier was broken. The supercharged air of the Carboniferous had unlocked a new potential, a new dimension of growth. And now, at the edge of that dark, acidic swamp pool, the time has come for the creature we met earlier, the patient, predatory nymph, to claim its inheritance. Imagine that hand-sized armored hunter after a year or more of prowling the murky depths, following a deep, ancient instinct. It begins its final journey, crawling slowly out of the dark, stagnant water it has always known. It climbs, gripping the rough, scaly bark of a giant lycopod tree or the thick, damp stalk of a colossal fern. It moves up, out of the water and into the air. And then it stops. It anchors its spiny feet firmly into the bark, a final solid grip on its old world. For a moment, it is perfectly still. Then, a profound and violent transformation begins. This is ecdysis, the shedding of its old self, and for an insect, it is an act of profound and terrifying vulnerability. A long, straight split appears down the back of its muddy, armored exoskeleton, and from within this old, dead shell, a new creature begins to pull itself free. It is soft, pale, and wet, its new body trembling with the immense effort. It pulls its long, slender abdomen free, and then, most critically, it extracts its 4 new, miraculous appendages. They are crumpled, thick, and useless, like wet pieces of paper. These are its wings. Hanging there, exhausted and defenseless, the creature begins to pump its hemolymph, its insect blood, into the fine branching veins of these crumpled wings. And as we watch, in the thick, humid air of the swamp, they begin to unfurl, to expand, to reveal their true, magnificent form. They are like intricate, wet maps of stained glass, a network of dark veins supporting a clear, shimmering membrane. They are vast. The creature will hang like this for hours, its new skin hardening in the oxygen-rich air, its wings drying, stiffening, becoming the powerful aerodynamic structures they were meant to be. And then it is ready. It takes its first breath of the supercharged air, not as an aquatic creature, but as a creature of the sky. With a single powerful muscular contraction, it launches itself from its old, discarded shell, its exuvia, and for the first time, it flies. This is Meganeura, or to be more precise, a member of the Meganeuridae family, the giant griffin flies. The name Meganeura itself means giant nerve, a name given by the French paleontologist Charles Brongniart, who was struck by the thick, intricate network of veins that gave its wings their incredible strength. And those wings are a spectacle. In our modern world, the largest dragonfly has a wingspan of about 7 inches. The wingspan of Meganeura was 2.5 feet, or 75 centimeters. This was an insect the size of a modern seagull or a hawk. Its body was long and slender, perhaps 1.5 feet in length, a streamlined, aerodynamic fuselage. It may have been brilliantly colored, a flash of metallic blue or iridescent green, a living jewel in the misty green twilight of the swamp. And at its head, 2 enormous globular compound eyes, each composed of thousands of individual lenses, giving it a near 360-degree view of its new kingdom, a world of potential prey and of limitless open air. It was no longer a nightmare in the water, it was the king of the sky. The image of a hawk-sized insect taking to the air seems, to our modern minds, to border on the impossible. We are used to the physics of our own world, a world where the laws of gravity and aerodynamics put a strict and heavy hand on the very idea of flight. For a creature to fly, it must generate a force of lift that is equal to or greater than the force of its own weight. For a large, heavy-bodied insect, this is a monumental challenge. And yet, Meganeura flew. It did not just glide. It did not just lumber through the air. The fossil record and its very body plan tells us that it was a fast, agile, and powerful flyer. It was an aerodynamic marvel. And it was made possible by a perfect confluence of 3 factors: a supercharged engine, a more forgiving medium, and a high-performance design. First, the engine. The flight of a dragonfly is one of the most energy-intensive activities in the entire animal kingdom. It is an act of pure, explosive power, requiring massive flight muscles that are packed into its thorax, or midsection. In a modern dragonfly, these muscles can make up over 1/4 of its entire body weight. Now, imagine the engine required to power a creature with a 2.5-foot wingspan. The muscles inside the thorax of a Meganeura would have been immense, a biological engine of incredible power. And in the Carboniferous, this engine was being fed a diet of rocket fuel. The 35% oxygen in the atmosphere meant that every breath the creature took was a jolt of pure high-octane energy. This supercharged air flooded its tracheal system, allowing it to power those massive muscles with an efficiency that no modern insect could ever hope to achieve. It had the raw power for flight. Second, it had the medium. The air of the Carboniferous was not just rich in oxygen, it was also denser than our modern air. This increased density, a result of the different mix of gases, meant that the air itself had more substance. It had more grip. For a flying creature, this is a profound advantage. Imagine trying to row a boat in a thick, viscous liquid versus trying to row it in thin, watery vapor. The thicker the medium, the more purchase your oar has, and the more thrust you can generate with every stroke. For Meganeura, its 4 great wings were like 4 powerful oars, and the thick, dense air of the swamp was the perfect medium to push against. Every single flap would have generated far more lift than it would in our thin, modern atmosphere. Flying in this world was simply easier. It was closer to swimming than to flying, a world of aerial buoyancy. Finally, it had the design. A dragonfly is not a plane, and it is not a bird. It is a biological helicopter, and a far more sophisticated one than any machine we have ever built. It has 4 wings, and it can control each of them independently. By beating its forewings and hindwings at different times and at different angles, it can perform feats of aerial agility that are almost magical. It can hover perfectly stationary in mid-air. It can fly straight up or straight down. It can fly backwards, and it can pivot, turning 180 degrees in an instant. Now, take that high-performance quadcopter design, scale it up to the size of a hawk, fuel its muscles with 35% oxygen, and set it loose in a thick, dense atmosphere that provides extra lift. What you have is not a clumsy, lumbering giant. What you have is a fast, agile, and terrifyingly effective flying machine. It was the undisputed master of this new, open kingdom of the air. And from its throne in the sky, it would have looked down upon the world of the swamp with one singular, all-consuming thought: to hunt. This new aerial kingdom was a world of opportunity, an open, 3-dimensional hunting ground, and Meganeura was perfectly, beautifully, and terrifyingly evolved to dominate it. It was not a gentle filter feeder, nor a passive grazer. It was an apex predator, the T-Rex of the Carboniferous skies. Its entire body was a weapon, a perfectly integrated system designed for one purpose: to locate, to pursue, and to kill other creatures in mid-air. Its primary weapon was its vision. At the front of its streamlined body were 2 of the most remarkable organs in the animal kingdom: its compound eyes. In a modern dragonfly, these eyes are a marvel, but in Meganeura they would have been a spectacle. Imagine 2 enormous, glistening globes, each one composed of thousands, perhaps tens of thousands, of individual hexagonal lenses. Each lens captured its own tiny pixelated image of the world. When these thousands of images were stitched together in the creature's simple but incredibly fast brain, it created a visual field of almost unbelievable quality. It was a near 360-degree panorama of its environment. It could see in front, to the sides, above, and almost directly behind itself, all at the same time. This visual mosaic was also acutely sensitive to one thing above all others: motion. The slightest flicker of a wing, the tiniest movement of a potential victim against the backdrop of the swamp, would have registered instantly. It was a living, breathing, all-seeing surveillance system. And it was fast. Its brain could process this information at a speed that is almost incomprehensible to us, allowing it to track and intercept a target with the precision of a heat-seeking missile. Imagine the hunt. From its perch on a high, dead branch of a scale tree, or perhaps as it hovered, perfectly stationary in the misty, humid air, its great eyes would have scanned the world. It was not looking for Arthropleura on the ground. That was a different world. It was watching the air itself, and the air was full of food. The Carboniferous skies were not empty. They were filled with a buzzing, whirring swarm of other large, primitive insects, flying cockroaches the size of your hand, and other, stranger flying creatures that have long since vanished. But perhaps its primary prey would have been other Meganeura, or its own smaller relatives. When it spotted its target, the pursuit was a masterpiece of physics. It did not simply chase its prey. It would calculate, with lightning speed, an interception course. It would fly not to where the victim was, but to where it would be, a complex feat of predictive 3-dimensional geometry. Closing the distance with powerful deep flaps of its 4 great wings, it would attack from below and behind, a blind spot for most flying creatures. It did not have claws or talons like a hawk. It had something far more specialized. Its 6 legs, which were useless for walking on the ground, were long, spindly, and covered in sharp, stiff bristles and spines. It held these legs cupped forward as it flew, forming a perfect, inescapable catching basket. In the final moment of the hunt, it would swoop upwards, scooping its victim out of the air in this spiny basket, the impact alone often stunning the prey. And from there, the end was swift. It did not need to land to eat. Still in full flight, it would bring its powerful serrated mandibles, its crushing saw-like jaws, to bear, dismembering and consuming its meal in mid-air. This was the king of the Carboniferous sky. A hawk-sized, precision-guided missile of an insect, a creature of near-perfect vision and lethal agility. It was the product of a supercharged atmosphere and 300 million years of evolution, a predator that ruled its domain without challenge, a living testament to the strange and terrible beauty of this lost and forgotten age. The Meganeura was the undisputed king of the Carboniferous skies, the high-speed, hawk-like predator that ruled the open air. But a king does not rule an empty court. The air of this ancient, oxygen-rich world was not a lonely void, punctuated only by the occasional griffin fly. It was a complex, bustling and crowded highway, a three-dimensional ecosystem filled with a whole other caste of giants that have long since vanished from the earth. Let us now turn our attention to one of the most successful and one of the strangest groups of insects from this time. They were so common that their fossils are a defining feature of the Carboniferous, yet they are so alien that they have no direct modern equivalent. They are the Paleodictyoptera. If Meganeura was the dragonfly, these were something else entirely. Imagine an insect, also of impressive size, with some species possessing wingspans of well over a foot, or 30 centimeters, but their design was fundamentally different. They were not built for high-speed, acrobatic pursuit. They were built to feed on the trees themselves. Their most defining feature was not their wings, but their mouth. Unlike the crushing, saw-like mandibles of the griffinfly, the Paleodictyoptera had evolved a sharp, rigid and needle-like beak, a formidable proboscis. They were, in essence, the first and largest of the true bugs. They were not hunters, they were drinkers. Imagine one of these large insects, perhaps a Mesotheiros, as it lands on the rough, scaly bark of a giant lycopod tree. It is not scanning the air for prey. It is searching for a place to feed. It would carefully, deliberately, plunge this sharp, hypodermic beak deep into the living tissue of the tree, piercing the tough outer layers to tap into the fluids circulating within. It was, in effect, a giant mosquito or a giant aphid drinking the blood of the colossal trees. But their strangest and most beautiful feature was in their wings. Most flying insects today, like all flying creatures, have one pair of primary wings, and perhaps a modified second pair, like the stabilizing halteres of a fly, or the hard, protective elytra of a beetle. The dragonfly has two high-performance pairs, but many of the Paleodictyoptera had 3 pairs of wings. In addition to their 2 large, veined and functional pairs of flying wings, they possessed a third, smaller, fixed pair. These were not true flapping wings, but rigid winglet-like lobes that grew from their prothorax, the segment just behind their head. Imagine a classic 4-winged biplane, but with an extra small set of fixed canards at the very front. Scientists still debate the function of these strange proto-wings. Perhaps they were used in courtship displays, a form of biological ornament. Or perhaps they were aerodynamic, acting as stabilizers, helping these large and perhaps somewhat clumsy plant feeders to remain steady as they came in for a landing on a branch, like the spoilers on a modern jet. So let us correct our mental picture. The Carboniferous sky was not an empty arena for the sole pleasure of the Meganeura. It was a complex and layered world. There were the high-speed carnivorous predators, And then there were these large, six-winged and beak-faced herbivores, gliding more slowly from tree to tree, living a quieter life as the first great plant drinkers of the air. The sky was a busy place. It was an ecosystem in its own right. And in a world this full of life, this full of giant, whirring and clicking creatures, the ancient, profound silence of the Devonian world was now well and truly broken. For so long in our journey into the deep past, we have spoken of the profound, almost sacred silence of the ancient world. The age of Prototaxites was a world whose only soundtrack was the sigh of the wind and the rush of water. But here, now, in the great steaming swamps of the Carboniferous, that eternal silence is finally and spectacularly broken. Let us stand still for a moment and simply listen. Imagine we are here as the day is ending. The sun is a dim, reddish disk, its light struggling to pierce the thick, permanent, humid mist that hangs between the colossal, scaly trunks of the lycopod trees. The air is so heavy, so warm, so laden with moisture and that potent, high-octane charge of oxygen that you can almost feel its weight on your skin. It is a global, tropical greenhouse. And the air is not quiet. It is alive with a sound that is both familiar and utterly alien. High above there is a deep, resonant and percussive whirring. This is not the gentle, high-pitched buzz of a modern insect. It is the sound of wings, great rattling, papery wings, 2.5 feet across, beating the dense air with ferocious power. It is the sound of Meganeura in flight, a sound like a badly made miniature engine or a large, rattling fan, a constant, intimidating presence in the upper canopy. Beneath this, from the treetops themselves, comes a different sound, a high-pitched, stridulating drone, a clicking, buzzing hum as the great six-winged Paleodictyoptera, the giant plant drinkers, move from branch to branch, their wings vibrating. It is the sound of 1,000,000 oversized cicadas, a chorus that fills the middle layer of the forest. And from the ground, from the dark, damp, spongy floor of peat and fallen fronds, other noises emerge. There is a slow, rhythmic, multi-legged scuttling, a sound of crushing and scraping. It is the sound of Arthropleura, its dozens of feet pressing into the damp earth, its broad, armored segments brushing against the giant ferns. It is a sound of immense, slow, and implacable weight, the sound of a living tank moving through the undergrowth. But there is another sound too, a new sound on the planet and one that is deeply familiar to our modern ears. From the dark, acidic, tea-colored water of the pools, a chorus erupts as the light fades. It is a wet, guttural croak, a series of plops and splashes. These are the amphibians, creatures like Areops, their great flat heads emerging from the water. These are the first true vertebrate voices on the land, a bubbling, resonant thrum of males calling for mates or for territory. And the smell of this world is overpowering. It is not the clean, earthy scent of a modern pine forest. It is the heavy, rich, and cloying perfume of a world that cannot properly decay. It is the sweet, sharp tang of fermentation, the smell of sulphurous mud, of damp, unrotted wood, and the deep, organic odor of 1 billion tons of peat, all hanging in the misty, supercharged air. This is the sound and scent of the Carboniferous, a world of giant rattling wings, of heavy armored footsteps, and the first wet songs of the vertebrate kingdom. It is loud, it is damp, it is teeming with a strange and supercharged life. But as the last light fades and the mist grows thicker, we are reminded that for all its vibrancy, it is also a world of incredible, hidden danger. For creatures this large, even the simple, necessary and private act of growing was a matter of life and death. This supercharged world of steam and giants was a kingdom of evolutionary opportunity, a place where the old rules had been suspended. But the laws of physics and biology, while they can be bent, can never be truly broken. For the giant arthropods of the Carboniferous, their immense size was their greatest advantage, but it was also their greatest and most terrible vulnerability. It was the source of a recurring life-or-death gamble, a biological price that every single one of them had to pay again and again. This was the price of the exoskeleton. An exoskeleton, the hard, chitinous suit of armor worn by all arthropods, is a biological marvel. It is a fortress, a solid framework that provides protection from predators and a firm anchor for muscles. But this fortress is also a prison. It is a rigid, unyielding cage. And because it cannot stretch, it cannot grow. In order to get bigger, an arthropod must perform one of the most dangerous and extraordinary acts in the natural world. It must shed its entire old self and grow a new one. This process is called ecdysis, or molting. In our modern world, we can see this small-scale drama play out in a summer garden. A cicada nymph, after years underground, will climb a tree, its back will split, and the winged adult will painfully, slowly pull itself free, leaving behind a perfect glassy shell. For a few hours, this new adult is a pale, soft and defenseless creature. Its wings crumpled, its body like wet paper, waiting for its new armor to harden. It is the most dangerous moment of its life. Now, let us take this small garden drama and scale it up to the titans of the Carboniferous. Let us imagine the sheer agonizing difficulty of this process for an 8-foot-long Arthropleura. The giant must first find a safe, hidden place in the deepest, most inaccessible part of the swamp. For days, its body has been preparing, a new, soft, wrinkled exoskeleton forming just beneath the old, hard one. A chemical signal is given, and the old armor splits along its back. And now, the true ordeal begins. The creature must, through a series of slow, rhythmic, muscular contractions, pull its entire colossal body out of its old self. Imagine the effort. It must extract, one by one, its dozens upon dozens of legs, pulling each one carefully from its old, hollow, chitinous stocking. It must pull its 8-foot-long, segmented body free, inch by agonizing inch. The process would take hours, perhaps an entire day, and it would be an act of profound, exhausting, and desperate effort. And when it is finally free, what is left is not a triumphant giant. It is a pale, quivering, 8-foot-long creature of jelly. Its armor is as soft as damp parchment. Its legs are too weak to support its own weight. It cannot move. It cannot fight. It cannot defend itself. It can only lie there, hidden in the mud, a helpless, breathing meal waiting for its new armor to sclerotize or harden, a process that could take many more hours or even days. In this state, it is a perfect target. A prowling pulmonoscorpius or even a large amphibian would see it as a banquet. Even a simple accident, a falling branch from a scale tree, could be fatal, its soft body offering no resistance. Imagine the Meganeura nymph, that hand-sized aquatic hunter. It too must molt again and again in the dark, predator-filled water of the swamp. It must split its old skin and emerge larger, softer, and more vulnerable than before, praying that no fish or amphibian finds it in those first critical minutes. The supercharged oxygen in the air and water would have helped. It would have fueled the immense metabolic energy required for this ordeal. But it could not speed up the slow chemical process of hardening. This was the great gamble of the giants. To live, they had to grow. And to grow, they had to risk everything, offering up their soft, defenseless bodies to a world full of dangers. Bigness was a gift from the atmosphere, but it was a gift that came with a terrible, recurring price. This delicate balance between opportunity and vulnerability could only be maintained for as long as the planet itself remained in its strange, supercharged state. And that state, like all states in the Earth's long history, was destined to change. For millions upon millions of years, the great coal swamps had seemed eternal. This vast, humid and stable world was the perfect cradle, an unchanging paradise that had allowed the arthropod titans to flourish and to reign. But in the long, slow story of our planet, nothing is permanent, and the very forces that had assembled this strange world were already, invisibly, beginning to tear it apart. The engine of this great change was not in the air or in the life forms themselves. It was in the deep, slow, grinding heart of the earth. It was the dance of the continents, plate tectonics, which had been in motion long before the giants and would continue long after they were gone. During the Carboniferous, the continents, which had been scattered across the warmer latitudes, were continuing their slow-motion, inevitable drift. The great southern supercontinent of Gondwana, which included the future lands of Africa, South America and Australia, was creeping steadily northwards. And in its path lay the continent of Laurussia, the landmass of North America and Europe. A collision was coming. This was not a sudden, violent crash. It was a slow-motion impact, a geological crunch that unfolded over tens of millions of years. As these two colossal land masses met, the earth between them had nowhere to go but up. The crust buckled, folded, and rose in a chain of new, immense mountains. This was the birth of the Appalachian Mountains in North America and the Variscan Mountains in Europe. In their youth, these were not the gentle, weathered hills we see today. They were a vast, towering and jagged range, perhaps rivaling the modern-day Himalayas in their sheer dramatic scale. This slow continental fusion, which would eventually link nearly all the land on Earth into the single supercontinent of Pangaea, had two profound and devastating consequences for the world of the giants. First, it eliminated their home. The great coal swamps thrived in the vast, low-lying coastal basins that had once dominated the world. But as the continents crashed together, these basins were destroyed, crumpled up and raised high to become the new mountain ranges. The very land upon which the swamps grew was vanishing. Second, it changed the global climate forever. It created a world of harsh extremes. A single, massive supercontinent has a vast interior, and this interior is a land that the ocean's moisture can never reach. The rain-bearing winds from the sea would drop all their water on the coasts, leaving the enormous heart of the continent to become an immense, arid desert. The age of the global humid greenhouse was over. It was being replaced by a new world, a world of dry seasonal extremes, of scorching summers and cold winters. The planet's great, wet heart began to dry out. The endless, steaming swamps that had once stretched from horizon to horizon began to shrink, to fragment. They broke apart, becoming isolated, damp pockets in a new, expanding world of dry plains and towering, rocky deserts. The era of the global swamp was ending, and for the creatures that had been so perfectly, so exquisitely adapted to it, this was a catastrophe. Their habitat was disappearing, but this drying of the world was only the first blow. It was a change that would trigger an even more deadly and even more direct assault on their very biology. The source of their superpower, the very fuel of their giant bodies, was about to be turned off at its source. The drying of the world was a catastrophic blow to the giant arthropods. As their vast, swampy kingdom shrank, their territory vanished and their populations began to fragment. But this loss of habitat, as devastating as it was only the first part of the assault. The changing climate was triggering a second, far more direct and far more lethal consequence. The very source of their power was being shut down. The atmospheric faucet that had been flooding the world with 35% oxygen was, for the first time in millions of years, being twisted shut. The reason for this was twofold: a devastating 1-2 punch delivered by the planet's new geological and biological reality. The first blow was the most direct. The high oxygen atmosphere was a byproduct of the great coal swamps. It was the result of a simple broken equation. Plants were producing oxygen, but the decomposers were not consuming it because the dead plants were being buried. Now, as the continents fused and the world grew drier, the swamps themselves were disappearing. The very engine of all that photosynthetic production was sputtering. With fewer swamps, there was simply less life pumping out that massive oxygen surplus in the first place. But the second blow was the final fatal one. It was an evolutionary solution to a problem that was tens of millions of years old. The problem of lignin. Remember that tough, woody polymer that the Carboniferous decomposers could not break down? Evolution, in its slow and patient way, had finally solved the puzzle. In the new, emerging world of the Permian period, a new kind of organism appeared, or rather, a new ability. A new family of fungi, the ancestors of our modern white rot fungi, had evolved the complex chemical key. They had developed a specific set of powerful enzymes, like peroxidase, that could do what was once impossible. They could dismantle, digest, and rot the stubborn, woody lignin. For the planet's great chemical cycle, this was a revolutionary moment. The great imbalance was over. The loop was finally closing. Now, when a tree fell, it no longer lay dormant, waiting for burial. In the new, drier forests, this army of new fungi would set upon it, and the wood would rot. And as it rotted, as the fungi decomposed the lignin and cellulose, they did so by breathing. They consumed oxygen and, in the process, released all of that carbon, which had been locked away for the tree's entire life, back into the atmosphere as carbon dioxide. The great burial was over. The age of sequestration had ended. The effect on the atmosphere was immediate and profound. It was being attacked from both sides. On one side, the great swamps were shrinking, meaning less oxygen was being pumped in. On the other side, the new, efficient decomposers were now busily consuming oxygen as they rotted the dead forests, meaning more oxygen was being pulled out. The concentration of oxygen in the atmosphere, which had soared to its giddy, life-altering peak of 35%, began a long, slow, and irreversible decline. It fell past 30%, past 25%. It began its long slide back towards the levels that we would recognize today, and perhaps, for a time, even lower. This was more than just a climate shift. This was a change in the very laws of physics that had governed this world. For the giant amphibians and reptiles, this thinner, less energetic air was a challenge, but for the giant insects, it was a death sentence. Their entire biology, their simple, passive, diffusion-based respiratory system was a miracle of engineering that worked for one reason, and one reason only. The air was so rich that it forced its way in. Now, the air was becoming thin, and for the titans of the Carboniferous, the very atmosphere they had been born into was, in a very real and terrifying way, beginning to suffocate them. The planet's atmosphere was thinning. The invisible, high-octane fuel that had powered an entire age of giants was being slowly, relentlessly diluted. For the titans of the Carboniferous, this was not an abstract, environmental change. It was a suffocating, physical reality. It was a noose, tightening with every passing millennium. To understand their plight, let us return to the fundamental, beautiful, and now fatal flaw of their design, the tracheal system. We must remember that this system of breathing was not an active engine, but a passive network. It was a delicate, branching labyrinth of hollow tubes that allowed the rich, dense air to simply diffuse into the body, seeping down to the deepest cells. It was a system that worked brilliantly if the concentration of oxygen outside was high enough to create the pressure needed to push it through the entire network. Now, that pressure was falling. The atmospheric push was weakening. Let us imagine this change from the perspective of a Meganeura, a giant griffin fly. In the golden age of 35% oxygen, every spiracle along its body was a high-pressure intake, flooding its massive flight muscles with more than enough fuel. It could fly with power, pursue prey, and live an energetic, high-performance life. But now, in this new, thinner air of the Permian period, its world has changed. With every breath it takes, less oxygen seeps into its tubes. The diffusion is slower. It is less potent. The air is no longer rocket fuel. It is a thinned, watery gruel. The first and most immediate effect would have been on its flight. The massive muscles in its thorax are the most energy-demanding in its body, and they are now being starved. It would have felt weak, heavy. Takeoff would have required more effort. Its flight would have become slower, more lumbering, less agile. That effortless, hawk-like pursuit, it was now a clumsy, exhausting chase. The supercharged engine was sputtering. On the forest floor, the same slow suffocation was happening to the Arthropleura. An 8-foot armored body requires an immense amount of oxygen just to perform the basic functions of life, to digest its food, to move its hundreds of legs. In the high-oxygen world, its simple tracheal system was up to the task. But in the new, thinner air, its deepest, most internal cells would have been the first to suffer. The oxygen, seeping in from the outside, could no longer make the long journey all the way to the center of its colossal body. It would have felt a profound cellular lethargy. Its movements, once a powerful fluid ripple, would have become slow and labored. And the greatest, most profound vulnerability would have been at the very beginning of its life. A large insect is at its most fragile not when it is an adult, but when it is an egg, and when it is a larva. An egg breathes through its shell. A larva, like the aquatic Meganeura nymph, breathes through the water. As the oxygen in the air fell, the oxygen dissolved in the water fell right along with it. The large, hand-sized nymphs in the ponds would have been the first to die, their simple gills unable to extract enough fuel from the oxygen-poor water. The large eggs of Arthropleura would have failed to hatch, their embryos suffocating within their shells. This was not a war with a predator. It was a war with physics, and it was a war the giants could not win. Evolution offered only one brutal solution. In this new, thinner atmosphere, the only individuals who could survive were the ones who were smaller. A smaller body meant a shorter distance for the oxygen to travel. A smaller body meant the tracheal system could once again be efficient. Generation by generation, natural selection began to favor tininess. The giants were an evolutionary dead end. The world that had invited them into being, the atmosphere that had fed them and allowed them to shatter the laws of biology, was now the very thing that was culling them from existence. They were, in the most literal sense, being erased by the air itself. The slow, invisible suffocation from the thinning air would have been enough in time to end the reign of the giants. It was a fundamental physical law that they could not escape. But evolution rarely, if ever, acts with just one force. As the world was becoming unlivable for the giant arthropods, it was simultaneously becoming the perfect, proving ground for a new kind of creature, a creature that would deliver the final competitive blow. Until this point, the dominant vertebrates on land were the amphibians, creatures like Eriops, with their great flat heads and sprawling alligator-like bodies. They were the masters of the swamp, moving between the water and the land. But they had a fundamental weakness, a chain that bound them forever to the water. They were tied to the pond. Their skin had to be kept moist to help them breathe. And most critically, their eggs were soft, gelatinous and jelly-like. They had no shell, no protection. They had to be laid in the water, or they would dry out and die in minutes. This was their evolutionary anchor. It meant they could never, ever truly conquer the new, drier continents that were forming. But life was already solving this problem. In the shadows of the coal forest, a new kind of animal was emerging, a small, lizard-like creature that had perfected a revolutionary piece of biological technology. It was an invention that would change the course of life on Earth forever. It was the amniotic egg. The amniotic egg was, quite simply, a private ocean, a personal life support system. It was an egg with a hard, leathery or calcified shell, a shell that could do what no amphibian egg could. It could hold in moisture. It could be laid on the dry, open land. Inside this protective shell, the developing embryo floated in its own private, fluid-filled sac, the amnion. It had its own rich food supply, the yolk, and it had its own specialized waste disposal sac, the allantois. It was a perfect, self-contained spaceship for one, a design that finally and decisively cut the ancient, ancestral tie to the water. This was the birth of the reptiles. Creatures like Hylonomus, a small, agile animal, perhaps the very first true reptile, could now do what no amphibian could. They could leave the crowded, dangerous and shrinking swamps and venture into the open, drier woodlands. These new reptiles had other advantages. They had developed more complex, more efficient lungs that were far better at extracting oxygen from the thinning air than the simple, bag-like lungs of an amphibian. And their legs were positioned more directly under their bodies, not sprawling out to the sides, giving them a faster, more efficient gait. Now, let us put all the pieces on the board. On one side, we have the giant insects. They are slow, weak and lethargic, starving for oxygen. Their massive bodies are a liability. Their molting process is a slow, agonizing period of total helplessness. On the other side, we have this new kind of creature, the first reptiles. They are small, fast and agile. They are fueled by efficient new lungs, and most importantly, they are land-based egg-eaters. The giants, in their weakened state, were no longer kings. They were a slow, defenseless and protein-rich buffet. The Arthropleura, once a gentle, unbothered gardener, was now a sitting target. Its soft, vulnerable eggs, even if buried, would have been an easy meal for these new, digging reptilian hunters. The giant, cat-sized scorpion, Pulmonar scorpius, once a top predator, was now slow and clumsy, its venom useless against these fast, scaly newcomers. And in the skies, the Meganeura, its flight now a slow, labored and inefficient buzz, was no longer a hawk. It was a target. The small, fast reptiles, with their quick-strike jaws, would have easily snatched the giants as they rested, weak and wheezing, on the branches of the ancient trees. The ecological guillotine had fallen. The very air was suffocating the giants from within, and a new, faster and more efficient predator had arrived to tear them apart from the without. The age of the insects was being replaced by the age of the reptiles. The changing world had passed a sentence on the giants. Their fate was sealed. The great unwinding of their empire, which began with the drying of the swamps and the thinning of the air, was now an unstoppable cascade. We were leaving the Carboniferous period behind and crossing an invisible geological boundary into a new age, the Permian. This transition, beginning around 299 million years ago, was not a sudden event. It was a slow, grinding and fundamental transformation of the entire planet. The great continental collision was now complete. The supercontinent of Pangaea had been born, a single, colossal, C-shaped landmass that stretched from the North Pole to the South Pole. For the first time in hundreds of millions of years, nearly all of the Earth's land was one. This new geography created a climate of brutal extremes, a climate that would be the final nail in the coffin of the old swamp world. The vast, mountainous interior of Pangaea was an immense continental desert, a place where rain never fell. The coastlines, which had once been vast, shallow basins, were now sharp and defined, with far less room for the humid, low-lying swamps to exist. And the global climate, which had been cooling since the forests first rose, now tipped into a full-blown ice age. The The southern half of Pangaea, which was still sitting over the South Pole, became buried under a sheet of ice larger than modern-day Antarctica. The world of the Carboniferous, that warm, wet, global greenhouse of a swamp, was gone. It was replaced by a planet of ice, desert, and a new, more resilient type of forest, one dominated not by the strange scale trees of the bogs, but by tough, hardy conifers, the ancestors of our modern pines, which were better adapted to the new, drier, seasonal world. And what of the titans in this new, harsh landscape? The fossil record tells the final, quiet chapter of their story. As we move from the rock layers of the Carboniferous into the layers of the Permian, the fossils of the giants simply and silently vanish. The great 8-foot tracks of Arthropleura are no longer seen in the ancient mud. The vast 2.5-foot wingspans of the griffinflies disappear from the record. The cat-sized scorpions are gone. But this was not an extinction, not in the traditional sense. It was a forced evolutionary retreat. Life did not vanish, it simply shrank. The lineages of these creatures survived. Dragonflies, millipedes, and scorpions, of course, are still with us today. But the gigantism itself, the very phenomenon that had defined an entire age, was over. The new, thinner air of the Permian was a permanent biological filter. It selected relentlessly for smaller and smaller body plans. The descendants of Meganeura were still flying, but they were now a fraction of the size, their wingspans shrinking generation by generation to a scale that their new, inefficient lungs could support. The descendants of Arthropleura were no longer kings of the forest floor, but tiny, humble, multi-legged decomposers, small enough to hide in the very leaf litter that their ancestors had once consumed by the ton. The giants did not go out with a bang, they simply faded away, shrinking back into the background of the ecosystem, their epic chapter closing with a long, slow, evolutionary sigh. They became the small, scurrying creatures we know today. Their reign was over. Their dynasty had fallen, and the world they left behind, this new harsh world of Pangaea, was now fully in the grip of their successors, the reptiles. But even this new world, this age of reptiles, was about to face a trial by fire, a planetary cataclysm so profound it would make all that had come before seem gentle by comparison. The Permian period had begun. The world had found a new, harsh and stable rhythm. On the single, vast continent of Pangaea, the age of giant insects was now a distant memory, a biological experiment that had faded with the changing atmosphere. The descendants of those giants, the smaller, more efficient dragonflies, millipedes, and scorpions, had survived, shrinking to fit their new oxygen-poor world. The reptiles, with their efficient lungs and amniotic eggs, were the undisputed masters of the new, dry landscape. Life, as it always does, had adapted. But the planet, this great, restless sphere of rock and fire, was not finished. The Paleozoic era, the old life era that had hosted the first fungi, the first forests, and the great arthropod titans, was about to come to a final, violent, and truly apocalyptic end. Life on Earth was about to face its greatest test, a cataclysm so profound, so all-encompassing, that it makes the asteroid that killed the dinosaurs look like a minor inconvenience. This was the Permian Triassic extinction event. We simply call it the Great Dying. It began around 252 million years ago. The trigger was not an impact from space. The enemy came from within. In what is now Siberia, the very crust of the Earth tore open. This was not a single conical volcano. This was a vast, sprawling fissure in the planet's skin, a volcanic province that covered an area larger than all of Western Europe. And it began to erupt. It did not stop erupting for perhaps 1 million years. It was an ocean of magma, a slow-motion, planetary-scale flood of lava that poured out, covering thousands of square miles in a layer of rock miles thick. But the lava was not the weapon. The weapon was the gas. From these fissures, the Earth hemorrhaged a truly inconceivable volume of carbon dioxide, methane and sulfur dioxide into the sky. The planet's delicate thermostat, which had been slowly cooling the world, was now seized and cranked, violently, in the other direction. A runaway greenhouse effect began. The planet started to heat up fast. The new, tough conifer forests that had adapted to the cool, dry world were burned away by relentless, searing acid rain as the sulfur dioxide mixed with the clouds. The food web on land collapsed, starting from the very bottom. But the true horror was in the ocean. As the planet heated up, the seas heated up with it, and warm water cannot hold dissolved oxygen. The oceans began to suffocate. They became vast, still anoxic zones, great purple pools of poisoned water choking the life from anything that couldn't escape. The dissolved CO2 turned the water acidic, and the shells of the countless creatures that lived there, from plankton to the great reefs, simply began to dissolve. It was the closest life on Earth has ever come to a total and complete reset. The statistics are numbing. An estimated 95% of all species in the ocean vanished forever. The trilobites, who had survived for 300 million years through ice ages and continental shifts, were gone. On land, 70% of all vertebrate life was wiped out. And what of our insects? The small, hardy survivors of the Carboniferous. They were hit just as hard. It was the greatest mass extinction of insects ever recorded. Many of the ancient lineages were extinguished completely. This was the final, brutal and definitive punctuation mark on the entire Paleozoic era. The world that had created the prototaxites, the world of the great coal swamps, the world of the supercharged air, and the world of the giant insects. That entire ancient chapter in Earth's history was now being burned, suffocated, dissolved, and buried. The slate was wiped almost completely clean, and from the ashes of this global apocalypse, a new world would have to be born. A new era, the Mesozoic, would dawn, and new rulers, the dinosaurs, would rise to claim a planet that had been scrubbed clean by fire and water. But the giants of the Carboniferous, though their bodies and their world were long gone, had left a deep and lasting gift, a silent, black inheritance buried in the rock, waiting for a future, conscious species to find it. The world had been reset. The Great Dying was a fiery and suffocating wall that separated the old life from the new. The Great Paleozoic era, the era that had hosted the silent fungi, the first forests, and the giant supercharged insects, was now definitively over. The titans were gone, their lineages shrunk, their kingdom a memory. But they had left a gift. Deep within the crust of the new world, buried under thousands of feet of new rock, the Carboniferous period had left a silent, black, and powerful inheritance. It had left a planetary-scale time capsule, a battery charged with 300 million-year-old sunlight. We call it coal. To understand this inheritance, we must return one last time to those misty, steaming swamps. We must picture those alien, 100-foot-tall scale trees, those lycopods and giant ferns living their lives. Every day they performed their quiet miracle. They breathed in the carbon dioxide-rich air, drank the swamp water, and, using the raw energy of the sun, they built their own bodies. They were, in the most literal sense, solid, physical sunlight. And when they fell, as we learned, they did not rot. They simply sank into the acidic, oxygen-starved water of the bogs, their lignin armor undefeated by the decomposers of their time. They piled up, layer upon layer, generation upon generation, in a thick, spongy, waterlogged mat. This substance, the first step in the process, is called peat. For millions of years, this was the state of things. But the world did not stand still. The continents continued their slow, grinding dance. The seas rose and fell. And these immense continental-sized peat bogs were buried. They were covered over geological time by new layers of mud, of sand, of silt, and eventually of solid rock. Imagine this peat, buried now, a mile deep beneath the surface of the earth. It is now subject to two immense and transformative forces. First, the colossal crushing weight of the world above it, a pressure so great it is difficult to comprehend. Second, the deep residual heat of the planet's core, a slow baking geological oven. For millions of years, the peat was cooked and squeezed. The pressure drove out every last drop of water. The heat broke down the complex molecules, driving off the volatile gases like methane and hydrogen. The very structure of the dead plants was rearranged, atom by atom. The water was gone. The gases were gone. All that was left behind was the one thing that truly mattered: the carbon. The soft, spongy, fibrous peat was compressed, hardened, and blackened until it became a brittle, glossy, and energy-dense rock. It was a battery, built by a forest, buried by a planet, and charged for 300 million years. And then, a tiny, fleeting fraction of a second later in geological time, a new, conscious species emerged: humanity. We, in our restless curiosity, found this strange, black rock. We discovered that, when touched by fire, it released its ancient, stored sunlight with a ferocious energy. We dug it from the earth, and with it, we fueled a revolution. The steam engines that built our modern world, the great steel mills, the first electric lights that banished the night, they were all powered by the ghosts of the Carboniferous. When you look at a piece of coal, you are not holding a stone. You are holding the physical, petrified remains of a lycopod tree. You are holding the branch that a Meganeura may have landed on. You are holding the stored sunlight of a day that dawned 300 million years ago, a day in the lost world of the giant insects. Our entire journey, this vivid portrait of a lost and alien world, is built upon a foundation of ghosts. We speak of these creatures with such confidence, describing the span of their wings, the armor on their backs, the way they hunted. But how do we know? How do we have such a clear picture of a world that vanished 300 million years ago? A world of creatures that were not built of sturdy, enduring bone, but of delicate, perishable chitin. A fossil, any fossil, is a miracle. It is a 1 in a billion chance, a perfect alignment of death and geology. For a large, heavy-boned dinosaur, the odds are low. For a soft-bodied, delicate creature like an insect, the odds are almost impossible. An insect's exoskeleton, that suit of chitinous armor, is strong in life. But in death, it is fragile. It is crushed, it is torn, it is scattered, and most importantly, it is eaten. Decomposers, the bacteria and fungi of their time, would have quickly set upon the remains, recycling them back into the ecosystem. For a giant insect to be preserved, it needed a very special kind of death and a very special kind of burial. It needed to die and fall into a place with no oxygen, a place where the bacteria could not destroy it. It needed to be buried, and buried quickly, by a fine, gentle, and particle-rich mud, a sediment that could capture the most delicate impression, like wet plaster taking a perfect mold of a feather. These rare, perfect burial grounds, these motherlodes of fossil preservation, are known to science by a German word, Lagerstätten, a storage place. And for the story of the Carboniferous, one Lagerstätte is more famous, more important than any other. It is a place in Illinois, in the United States, known as Mason Creek. Today, Mason Creek is a quiet river valley, its banks littered with old coal mining spoils. But 300 million years ago, this was a vast, muddy, coastal delta. It was the place where a great river flowing out of the coal swamps met a shallow tropical sea, and in this muddy, brackish water, a unique kind of chemistry took place. Here is what would happen. A Meganeura, its long life at an end, would fall from the sky. It would land not on the forest floor where it would be eaten, but in this soft, iron-rich delta mud. It would sink and be quickly covered by the next layer of silt. Then, the magic would begin. As the delicate body of the insect began to slowly decompose, this process released a small cloud of carbon dioxide. This carbon, in the low-oxygen mud, reacted with the iron in the surrounding water. This chemical reaction caused a new mineral, iron carbonate, to precipitate out of the water, forming a hard, dense and protective shell around the decaying insect. The creature had, in effect, built its own coffin, its own stone time capsule. This is called a concretion or a nodule. And for 300 million years, the giant insect lay entombed in this small, oval, rocky vault. Today, fossil hunters walk the spoil heaps of Mason Creek, and they are not looking for fossils. They are looking for these nodules, these simple, unassuming, rust-colored, oval stones. They look like nothing, just river rocks. But the hunters collect them and take them home. And in the winter, they will subject them to a repeated cycle of freezing and thawing, a process that gently, patiently, cracks the rock along its hidden internal line of weakness. And then, one day, with a small, soft pop, the stone will split in half like a locket. And there, pressed between the two halves, is a perfect, dark, S-negative image of the creature that died that day. It is a carbon film, a shadow in the stone. We can see the full, breathtaking span of the Meganeura's wings, the fine, intricate veins, the segments of its body, the very bristles on its legs. This is how we know. We are not guessing. We are looking at a 300 million year old photograph, a perfect, miraculous shadow, the last and only testament of the giants that once ruled the world. And these shadows, when compared to the giants of our own time, show us just how much the world has truly changed. The fossil record, those beautiful dark shadows in the stone, paints a picture of a world of titans that is now long gone. But it begs a natural question. Has life not tried again? Does our own modern, vibrant and incredibly diverse world not have its own giants? The answer is yes. We do, but they are giants on a very, very different scale. If you were to travel to the humid, tropical rainforests of equatorial Africa, you might hear a low, heavy, droning buzz, a sound like a small, struggling engine. This is the Goliath beetle, the heavyweight champion of the modern insect world. It is a creature of immense bulk, its body as thick as a man's thumb, and weighing in its larval stage as much as 100 grams. As an adult, it is a beautiful armored jewel, its heavy, powerful wings carrying a body that feels more like a small rodent or a large bird in your hand than an insect. Or if you were to explore the remote forests of New Zealand, in the deep, damp darkness, you might find the weta, a giant, cricket-like creature, ancient and solitary. The giant weta can weigh more than a sparrow, its spiny, armored body a magnificent example of island gigantism, a place where, for millions of years, there were no small mammal predators, allowing it to grow to the very limits of its form. In the rainforests of Southeast Asia, you might mistake a twig for a living creature until that twig begins to move. This is the Chan's megastick, a stick insect that can reach a total length of over half a meter, or nearly 2 feet, a long, delicate, and almost impossibly strange creature. And in those same forests, at night, you might find the Atlas moth, a giant of the sky, its broad, beautiful fur-covered wings spanning nearly a foot or 30 centimeters across. These are the champions of our time. They are awesome, beautiful, and push the very boundaries of modern biology. And yet, When we place them in our imaginations side by side with the titans of the Carboniferous, the comparison is almost poignant. That beautiful Atlas moth, a giant in our world with its 1-foot wingspan, would be utterly dwarfed, a mere snack for a Meganeura with its 2.5-foot span. That heavy, bulky Goliath beetle, which can rest in the palm of your hand, is a grain of sand next to the 8-foot, car-sized Arthropleura. So why the profound difference? Why are our modern giants so profoundly smaller? The answer, once again, is in the air we breathe. Our 21% oxygen is not an enabler, it is a cage. The simple passive tracheal respiratory system, which was the giant's greatest asset in a supercharged world, is their greatest prison in ours. The Goliath beetle, the waiter, the Atlas moth, they are not small. They are the absolute maximum. They are the creatures that have pushed their biology to the very, very edge of what is physically and mathematically possible in our thin modern air. They are a living, breathing testament to the ironclad atmospheric limit. The fossils of the Carboniferous are the testament to the one brief, spectacular moment in time when that limit was broken. But this begs a fascinating modern question. Is this limit truly permanent? Is it just a theory? Or if we could somehow replicate that ancient oxygen-rich world in a laboratory, would the giants begin to return? The story is compelling. It is a neat, elegant, and powerful theory. The simple, passive breathing system of an insect is a cage. Our modern 21% oxygen atmosphere is the bars of that cage, setting a hard limit on size. The 35% oxygen of the Carboniferous was the key that unlocked that cage, allowing the giants to walk free. It is a beautiful story. But in science, a beautiful story is not enough. It must be tested. How could you possibly test a hypothesis that is 300 million years old? We cannot, of course, travel back in time. We cannot rewind the planet's atmosphere. But what we can do in the quiet of a modern laboratory is rebuild a small piece of that ancient world. We can, in essence, build a time machine in a box. This is exactly what scientists like John Harrison at Arizona State University and Robert Dudley at UC Berkeley set out to do. They decided to test this great atmospheric hypothesis in the most direct way possible. They would try to raise the giants again. Their setup was beautifully simple. They took modern insects, the direct living descendants of those Carboniferous creatures. They used dragonfly nymphs. They used the larvae of beetles, they used fruit flies, and they divided them into groups. One group, the control group, would be raised in a normal, modern world. Their plexiglass enclosures would be filled with the air we breathe right now, 21% oxygen. The other groups would be raised in a very different world. Their enclosures would be sealed, and a carefully controlled mix of gases would be pumped in, a mix that was a precise, chemical echo of the deep past. One of these enclosures would be a tiny sealed Carboniferous world, its atmosphere held at a potent 35% oxygen. Then the scientists simply waited. They raised these insects generation after generation in their artificial worlds, letting evolution and biology do their work. And the results were stunning. The dragonflies that were raised in the high-oxygen Carboniferous in a box environment grew bigger. They did not, of course, grow to the size of hawks. The experiment did not run for 1 million years, and their modern genes have been shaped by 300 million years of living in a thinner world. But they grew measurably, significantly larger than their brothers and sisters in the modern air box. In some cases, as much as 15% larger. The theory was holding. The increased oxygen allowed them to break their modern size barriers. They tried it with beetles. The mealworm beetles raised in the ancient atmosphere also grew larger than their modern counterparts. The high-octane air was, just as predicted, removing the bottleneck. It was supercharging their simple, passive breathing, allowing them to support a larger, more massive body. The theory was not just a story. It was a visible, measurable biological reality. But the experiments also revealed a beautiful and unexpected layer of nuance. Not everything grew bigger. The fruit flies, when raised in the 35% oxygen, actually evolved to become smaller. This was, at first, a baffling result. Why would a supercharged atmosphere, the very thing that created giants, cause these tiny creatures to shrink? The answer is a reminder that oxygen is not just a fuel. It is a fire. It is a volatile, corrosive, and dangerous gas. It creates free radicals, rogue molecules that can tear apart cell membranes and damage DNA. This is called oxidative stress. It is the very reason we age. For the dragonflies, the benefit of the extra fuel for their large bodies outweighed the cost of this oxidative damage. But for the tiny, fast-living fruit fly, the 35% oxygen was not a gift, it was poison. It was too much of a good thing, a flood of corrosive, toxic fire that was damaging their tiny bodies. And so, in a beautiful act of microevolution, they adapted by becoming smaller, their bodies more efficient, their metabolic engines tuned down to better cope with the stress of this dangerous, supercharged air. The experiments were a perfect two-part confirmation. Yes, oxygen is the great enabler. It is the key that unlocks the cage of the tracheal system and allows gigantism to happen. But it is also a dangerous, toxic filter. Life must be perfectly, exquisitely tuned to the amount of oxygen it has. The potential for gigantism, it seems, is still written in the genes of every insect on Earth, a sleeping memory of a time when the air was different. The experiments proved it. So this leads to one final fascinating question. If the oxygen in our atmosphere were to somehow rise again, would the hawk-sized dragonflies and the car-sized millipedes return to rule the Earth? The answer, we now know, is no. And the reason is not in the air. The reason is in the sky. The modern experiments are a fascinating glimpse into a what if. They prove that the ancient genetic potential for gigantism is not truly lost, but merely dormant, a sleeping ghost in the code of every dragonfly and beetle. They prove that if you provide the fuel, if you recreate that Carboniferous in a box, life can and will respond to the opportunity. So let us ask that question one last time. If, by some unimaginable, planet-scale event, our atmosphere were to once again become supercharged with 35% oxygen, would the age of Titans return? Would our skies in a few million years once again fill with hawk-sized dragonflies and our forests crawl with car-sized millipedes? The answer is a definitive and resounding no. The Carboniferous period was a perfect storm, a unique, magical, and unrepeatable moment in the history of life. And what made the giants possible was not just one ingredient, but two. The first, as we have explored, was the physical ingredient, the high-octane, oxygen-rich air. This was the invitation to gigantism. But the second, and arguably more important, ingredient was the ecological one, an empty sky. When Meganeura unfolded its wings and launched itself from that swampy log, it was a pioneer. It was the first creature on Earth to truly master powered flight on a large, predatory scale. The air was a new, open frontier, a vast, three-dimensional kingdom with no king. It was the apex predator of the Carboniferous sky for one very simple reason. It was the only predator in the Carboniferous sky. It had no rivals. It had no competition. The niche was open, and it filled it gloriously. Today, that niche is not just full, it is occupied by some of the most sophisticated, high-performance and intelligent flying machines that evolution has ever produced. The invitation of high oxygen may be gone, but more importantly, the opportunity is gone forever. First, there are the birds. They are the living descendants of the dinosaurs, and they are, pound for pound, the most efficient, warm-blooded flyers on the planet. A Meganeura flew on a simple, passive and inefficient breathing system. A modern hawk or an eagle has a hyper-efficient one-way flow avian lung, a biological marvel that extracts nearly every molecule of oxygen from every breath, allowing it to fly at high altitudes and perform feats of incredible endurance. A Meganeura was cold-blooded. Its power, its very ability to move, was dependent on the warmth of the sun and the air. A bird is a warm-blooded endothermic furnace, its muscles hot, its metabolism roaring, ready for high performance, explosive action at a moment's notice, day or night, in warm air or in cold. And most critically, a bird has a brain. It has a complex, intelligent, and fast-processing mind, capable of learning, of strategy, of complex, predictive hunting. Imagine a revived Meganeura trying to exist for even one day in a modern sky. A peregrine falcon, a warm-blooded, intelligent killer, diving at over 200 miles an hour, would snatch it from the air before the giant insect's slow, primitive brain had even registered the shadow. A simple crow, with its problem-solving intelligence, would hunt its nymphs and raid its eggs. The giants would be an easy, slow, and stupid buffet for the kings of the modern sky. And even if by some evolutionary miracle, a new giant insect evolved to fly only in the darkness, to hide from the birds, the night sky is also full. It is owned by the bats, another warm-blooded, agile and efficient flyer, but one armed with a superpower that is almost alien in its perfection: echolocation. A giant, fluttering, soft-bodied insect would be a deafening, unmissable, brightly lit target in the sonar world of a bat. The Carboniferous was a window, a brief 100 million year-long window where the physics of the atmosphere provided the invitation and the ecology of an empty world provided the opportunity. That window is now and forever closed. The physics have changed and the opportunity is gone. The sky is full and it belongs to the quick, the warm, and the smart. The age of giant insects is locked firmly in the deep past, a spectacular memory of a time when the world was new and the air was open to all who dared to claim it. And so, our long journey into the steamy, misty, and buzzing world of the Carboniferous comes to an end. We have walked beneath the alien, 100-foot-tall scale trees. We have listened to the heavy, rattling wings of hawk-sized predators, and we have stood in the shadow of armored giants that crawled the forest floor. We have, for a time, breathed the air of a different, supercharged planet. The story of the giant insects, like the story of the fungal titans that came before them, is at its heart a story of air. It is a profound meditation on the beautiful, intricate, and sometimes terrible dance between life and the planet it lives on. Life is not a passenger, simply existing on the Earth. Life is the Earth. It shapes its environment, and the environment, in turn, shapes it. The first great forests, in their triumphant green conquest, rewrote the sky. They created an atmosphere of such potent, fiery energy that it invited a new, fantastic kind of life into being. And that life, the giant arthropods, rose to the challenge, becoming the perfect, monstrous, and beautiful expression of that unique and fleeting moment. And when the planet changed, when the air thinned and the world dried out, the giants, in their turn, faded with it. They were a perfect answer to a question the planet is no longer asking. The next time you are in a garden on a warm summer evening and you hear the high-pitched, whirring buzz of a dragonfly as it darts past you, pause and listen. You are not just hearing an insect, you are hearing a living, breathing echo, a faint molecular memory of a 300 million-year-old dynasty. You are hearing the whisper of a creature that was once a king, a creature whose ancestors commanded the skies with the power of a hawk, a creature that is now bound perfectly and elegantly by the thin, calm and gentle physics of our modern air. The Earth is patient, its history is deep, and its memory is long, and in its silent planetary way it is always dreaming of new forms, new worlds. The titans of the coal swamps are gone, but the hum of their wings, the faint resonant buzz of their long-lost age can still be heard if we listen closely in the profound and peaceful silence of deep time.